Welcome back. I wonder how this went for you. Let's go through it together. To find equilibrium solutions, we're going to take the formula for our derivative, our y prime, and set it equal to 0. And I'm calling the y's y hats because that's our notation for equilibrium solutions. So either y hat plus 2 equals 0, or y hat squared minus 6 equals 0. By the way, the way I got this y plus 2 equals 0 is either one of the two factors has to be 0. So if you think of one factor as y hat plus 2 squared, then you square root both sides and you get back to y hat plus 2 equals 0. That would give us y hat equals negative 2, and the other possibility, y hat squared equals 6. So y hat could be positive square root of 6, or y hat could be negative square root of 6. Now we want to get the phase plot, which I did do in GeoGebra, and I got something shaped kind of like that. That was supposed to go all the way up and touch the horizontal axis. Speaking of which, we should label these. Our horizontal axis is representing y's, and our vertical axis is y primes. Our equilibrium points are the places that the graph crosses the horizontal axis, which is going to be at negative root 6, and at negative 2, and at positive root 6. Now putting the arrows in, let's see, negative root 6 is a stable equilibrium because the arrows are pointing towards it. What about negative 2? That one might have puzzled you because it has arrows pointing towards it from the right, but away from it on the left. Well, the way it works is if any arrows are pointing away from the equilibrium, it's unstable. Because what that would mean is if the y value is a little bit less than negative 2, say it was negative 2.1, it's not going to return to negative 2, it's going to go in the other direction. If it's not stable from both sides, we can't say it's stable, we have to say it is unstable. So we're going to have to say this one is unstable. And last, the positive square root of 6, that's definitely unstable. It's got arrows going away from it in both directions. Let's look at some examples that are more applied now. The first example has to do with infectious disease dynamics. So one model that's often used to model the spread of an infectious disease is di dt equals beta I times n minus I minus mu times I, where I is the number of people infected, beta is some constant determined by the rate of transmission, mu is the rate at which people recover from infection, that's also a constant, and n is the total size of the population being modeled. We're first given some values to put in for the constants. So we're now looking at di dt equals 0.01 I times 1000 minus I minus 2I. We want to construct the phase plot, find the equilibrium solutions, and determine their stability. I'm going to go over to GeoGebra to do that. I've entered our formula using x's, 0.01x times 1000 minus x, and then minus 2x. I probably need to zoom out to get a better picture of what's going on here. Yeah. I don't know if you noticed, but we should have been expecting a parabola because if you multiply the 0.01x into the parentheses, you'll get an x squared term. I'll go ahead and screenshot this, being careful to get the important features of the graph in, like where it crosses the x-axis. And there's our phase plot in the notes. Let's find the equilibrium solutions now. I'm going to set my derivative formula equal to 0. I need to get this factored. I can tell it's not factored because of that minus sign right there. To do this, we'll distribute the 0.01 I hat into the parentheses. That will give 10 I hat minus 0.01 I hat squared minus 2 I hat equals 0. We'll combine like terms, which will give us 8 I hat minus 0.01 I hat squared equals 0. And now we can factor. We've got a common factor of I hat that we can take out, which will leave us 8 minus 0.01 I hat equals 0. So either I hat equals 0 or 8 minus 0.01 I hat equals 0. And if we solve this for I hat, we'll get 800. So those are our two equilibrium solutions. The one at 0 is pretty clear on the plot, but I'm going to go ahead and label this one as 800. Now I need to put in the little arrows. Oh, and I should label my axes. Let's see, the horizontal axis is the I-axis, and the vertical one is the I' axis. The equilibrium at 800 has arrows pointing towards it from both sides, so that one is stable. The one at 0 has arrows going away from it, so that one is unstable. Next, we want to do the same thing, but leaving the constant values unspecified. So this time we're working with the original differential equation with nothing to put in for the constants. So we're back to just having beta I and minus I minus mu times I. There's no way to enter a formula like this in GeoGebra, or really any grapher, without specifying values for the constants. But the good news is we can use what we already did in GeoGebra to get a phase plot even for this situation. So let me show you how to do that. We can go ahead and use this exact same graph. We just need to get rid of all the numerical labels on the axes because they won't apply to other choices of constants, and they certainly won't apply to just unspecified constants. So I'm going to go into the settings. I'm going to turn off the grid. On the x-axis, I'm going to uncheck Show Numbers. And on the y-axis, I'm also going to uncheck Show Numbers. And that's all we really need to do to adapt the phase plot we had before to a more general one. Now we need to find the equilibrium values. So I set my formula with the hats equal to 0. Again, this is not factored because of that minus sign in front of the mu I. So in order to get this factored, I will need to distribute the beta I hat into the parentheses. Then I'll combine like terms. So by like terms, I mean the ones that both have I hats in them and not I hat squared. That first one, beta I hat n, I can think of as beta n I hat, and then I'm subtracting from it mu I hat, and we also have minus beta I hat squared equals 0. And now to combine these first two terms, one way to think about it is you can say, oh, I'm going to factor the I hat out. So I'll have beta n minus mu times I hat minus beta I hat squared equals 0. And now we have two kind of giant terms, if you want to call them that, an I hat term and an I hat squared term. So I'll factor an I hat out of those two. That'll leave me I hat times beta n minus mu minus beta I hat. So either I hat equals 0 or beta n minus mu minus beta I hat equals 0. And if we solve that for I hat, let's see, I'll add a mu to both sides, I'll subtract a beta n from both sides, and I'll divide out the minus beta that's on the I hat. Oh, and this would be a little cleaner to write as beta n minus mu over positive beta. So our first equilibrium is at 0, and our second one is at beta n minus mu over beta. And then putting the arrows in, we can see that the equilibrium at 0 is unstable, whereas the equilibrium solution beta n minus mu over beta is stable because the arrows are pointing towards it from both sides. Oh, and I almost forgot to label the axes.